Formerly meant to be a BLDC motor, this ISB evolved into what is known as an axial flux alternator. This type of electromechanical conversion machine is best described a low-speed pancake generator, as it produces surprisingly high amounts of no-load voltage with relatively low RPM, and it is flat like a pancake. So first, the design was begun with the accommodation of rectangular permanent magnets in the rotors. The magnets used in this build are 20 by 40 millimeter N35 neodymium magnets. The rotor was designed such that 8 magnets fit around in a circle. The next thing to consider was how to optimize the linkage of magnetic flux lines between magnets of opposite polarity, both on the same rotor and across to the opposite rotor. This drawing hopefully illustrates the analogy between current in an electric circuit and flux density in a magnetic circuit. Magnetic permeability is a material's ability to create internal magnetic fields when in the presence of an external magnetic field. The permeability of free space is a constant mu0, which is a very small number. This is problematic as the magnetic flux from each permanent magnet must link up with the two magnets that are adjacent to it and the one that is opposite to it. So, a giant zinc-plated carbon steel washer is used on the back of each rotor to facilitate this linkage, as it has a permeability 100 times greater than that of free space. The combination of N35 grade rare earth magnets and this steel rotor yoke yields an insanely strong magnetic attraction between the two rotors at close distances, which is one of the most important factors in the performance of a generator. With this part in mind, a rotor back iron holder was designed, which fastens onto the rotor using 8 M4 bolts evenly spaced on the circumference of this part. The stator is designed with 6 coils, 3 phases, and 2 poles for each phase. The center of coil B is at an angle of 2 pi by 3 radians from coil A, and coil C is at negative 2 pi by 3 radians from coil A. This causes the 3 phases, EMF, and current outputs to be out of phase by the same amount, 2 pi by 3. The stator, as the name implies, is meant to be kept stationary while the rotor rotates around it. It achieves this with an 8 mm open ball bearing, which is friction fit in place in the center of the stator. Next, the 6 electromagnet coils are wound using copper wire. Faraday's law describes how a change in magnetic flux through a cross-sectional area of a coil will induce an electromotive force that is proportional to the number of turns of the coil. When the magnets are spun faster, this produces a higher voltage, as the time it takes for the magnet to pass over a coil becomes shorter. With this information, the EMF graph can be understood. Because the amount of voltage produced is directly proportional to the amount of area that the magnetic flux passes through, the peaks are when the south pole of a magnet is in the center of a coil, or pair of coils in a phase, really. This is because a south pole is just a magnetic field with a strength of negative teslas. Thus, the negative signs will cancel in the equation for Faraday's law, and the EMF will be at a peak value. Alternatively, when a north pole is at the center of a pole pair of a phase, EMF is at a low value. The coils were carefully designed according to the magnet topology. Winding a couple test coils, I realized that the only way to have a consistent shape, and thus consistent phase voltage, was to make each coil around a uniform coil skeleton. The procedure for winding a coil was as follows. First, I would mount the coil skeleton on the coil winding mechanism. Next, 21 gauge wire was placed on the spool holder and clamped to the desk. Afterwards, the first couple of turns were made using pliers, and then the end of the coil was tied in place. By rotating the coil former by hand, 63 turns of copper wire were made per coil. The turns were carefully made with a lot of tension so as not to overlap too much, as this reduces efficiency, and the completed coil was extracted using a shield of electrical tape and then wrapped in electrical tape. In this 3-phase generator, Y configuration is used. Y configuration has an optional neutral wire at the junction of all 3 phases. It also has the ability to get a phase voltage or a line voltage. All this knowledge is synthesized in the final design. Thank you for watching.